want this to be a little interactive, so please use the chat. And how many of you know about time complexity already? Like, just type a yes or a no in the chat. Like, how many of you have encountered this before, have actually used it when you're coding? You've thought about it. Vibali says yes. Of course, you're in second year. First years, what's the status on your side? Have you guys done it before? Right, first years are unresponsive, so the session will be okay. Pragya says she has done it before. Cool. So this will not be just a basic overview because I assume a lot of you will have done it before. So yeah, a lot of you know it, and so I decided to take this to like one step forward. So we're going to be discussing a few more things in theoretical computer science that's related to time complexity, but you might not have done it already. So let's get started. So the first thing we need to know is what is an algorithm. An algorithm is a series of steps to achieve a task, to perform a task. And when we're writing programs, we're basically coding the algorithm into something executable. So we all know what an algorithm is. We're familiar with those things. We've written codes before. And what is time complexity? Time complexity is a measure of growth in an algorithm. So what do I mean by growth? When an algorithm has an input and an algorithm has an output, and to compute this output, the algorithm takes a certain amount of time. When the input grows, how is this execution time growing? We need to find that out. That is what we're interested in. So that is what we mean by growth. How do we find the execution time? How do we make an estimate of that? Because calculating time is not easy. So suppose we do that with the number of operations, because operations take time to be executed. Now suppose one operation takes a constant time x to be executed. 10 operations would take 10x time. Similarly, 50 operations would take 50x time. So if we can find the number of operations, if we can count that, then we can get an estimate of the time because it's directly proportional. And why is time complexity important? Time complexity is important because we are not going to be writing programs for C lab forever. We are not just going to write programs where we have to find the sum of all elements in an array and the array is of size 10 or something. We will, some of us is where we'll be building products used by millions, billions of people. And when that happens, there's going to be a lot of data, there's going to be a lot of input. So the input size grows almost infinitely. And then if your algorithm is not efficient, if your algorithm is not optimized, that will be a huge waste of time, and time is an important resource. So time complexity is something that especially companies place a lot of emphasis on because companies build products and products need to be fast. When we talk about time complexity in computer science, we are interested in asymptotic time complexity. So what is asymptotic? Something that tends to infinity and stabilizes. So we're not interested in small values of n, where n is the input. We are not interested in places in, like, suppose you're sorting an array and the array is of 3 elements. We don't want to know the time taken to sort 3 elements, but we do want to know the time taken to sort, say, 1 million elements. We're not interested in the small picture. We want to know when this n grows infinitely, how is my performance? How is my algorithm doing? So, when I am mentioning time complexity today, we will be talking about asymptotic time complexity. Just assume that whenever I say time complexity, it's asymptotic. And a lot of us are familiar with this called the big O notation. It is actually the worst case scenario, and I will be expanding on that more in a little while. Now, suppose you have time complexity is nothing but a function. It is a mapping of the input to the performance. So we can think of it as a function f of n, where n is the input, and it gives us a measure of the performance, which is in terms of a function. Any function can be plotted on a graph. And when you're plotting this function on the graph, you get a curve. And this curve tells you how your algorithm is performing with varying input. Now here I've taken an example. F of n is equal to 3n log n plus 10n plus 2. When I'm finding the big O notation of this, it's only n log n because I'm only interested in the growing function. I want to know the maximum growth. What is the worst case? So n log n is the upper limit. It is the term that makes the largest impact on the growth of the function. And that's why that is all we want to know. Because, like I said, we are interested in asymptotic behavior. We want to know what happens in infinity. We don't want to know what happens for small values of n. So, at infinity, the term that will affect our performance the most is n log n. And that's why we will be interested in n log n more. Now, we've all done optimization. We know this, that efficiency is important. Suppose you're taking a maths exam and you have to add 107 plus 63. Well, one way you could do it is add 1, 2, 3, 63 times you add 1 to 107. Or you could do even worse. You could add 107 times to 63. Can you imagine how much time that would take? It would take a lot of time. You can actually code this with a computer as well, and it would take more time. Instead, you could just use whatever you've learned in high school, and you would do it in like a few seconds. And if you were to use the first method, you might not even be able to submit your paper on time. So that's something we want to avoid. Efficiency is something we all want to incorporate in our lives. Now, the three notations that we commonly use when we are talking about algorithmic analysis, time complexity, is big O, big omega, and big theta. Now, big O is the one we're probably most familiar with. As I've mentioned a while before, big O notation is the upper bound. It is the worst case scenario. What happens in big O is we are finding a function which is always performing worse than our algorithm asymptotically. As you can see in this graph, there will be values of n where my function is actually performing worse than the function chosen in my big O notation. But that is not the case for all values above n naught. As you can see, there's an n naught here. So for all values above n naught, which means as n grows till infinity, the big O notation always performs worse than our algorithm. And that's what we're interested in. We are not interested in what happens in small values of n. Why we work with the big O notation is this gives us the worst case scenario, the upper bound, which means it's a guarantee that our algorithm will never do worse than big O. And this is important in places like competitive coding, where you have to, suppose, pass a time limit. And you want to know what's the worst situation, what's the worst your algorithm can do. So in that situation, we rely on the big O notation. Another notation is the big omega notation. It's exactly like big O but reverse. Here we are choosing a function which will always perform better than our algorithm. So this is the asymptotic lower bound. It's the best case scenario. So again, it's just similar to big O. It just does better instead of worse. And then there's another notation, big theta, which is used a lot in theoretical computer science because this is the average case. We find two functions, and these two functions actually it's one function but multiplied by two constants. And this function bounds our algorithm. Our algorithm cannot do worse than C2 of that function and cannot do better than C1 of that function. Another thing is important when we're considering time complexity. We really ignore constants because constants do not grow. Constants are just constant, they don't change with the input. So since we're only bothered about the growth, we ignore constants. They are constant, we don't care about those. So big theta is actually used a lot when we're making some proofs. Sometimes when we're solving recurrence relations, you'll be learning more about that in second year. And the thing is, there's a misconception that the best case is represented by big omega, worst case by big O, average case by big theta. But like I just said those things, right? You might be confused that I just said that this is best case, worst case. Why am I saying that these three notations represent those? Um, the thing is, you can use any notation to represent best case, worst case, or average case because these notations are interchangeable. You can change from one notation to another. And we often do that when we are proving theorems. We actually sometimes change from big O to big theta, depending on what we're trying to prove. So this is a little theoretical, and don't worry too much about that. You'll learn more in second year, third year. Now, one of the best performing time complexities is constant time. Now, I have an example program for you. Suppose X is your input. So we have one operation which takes input for X. We have one operation which assigns to X, one operation which accesses the value from X, and one operation which adds 1 to X. And then we have one operation which prints X. So that is a total of 5 operations. And but the thing is, when I'm giving 3 as input for X, the output is 4. If I give 15, the output is 16. If I give 71, the output is 72. But the number of operations is always 5. That does not change, that is constant. So we call this O1 complexity in the big O notation because no matter how my input grows, the number of operations does not grow, it's constant. Then we have linear time complexity, where suppose n is your input and you're finding the sum. Uh, suppose you're finding a linear sum, suppose a sum of all elements in an array, and you have a loop which goes from 0 to n minus 1. So that's n times the loop is running n times. And for each of the n times, you are performing an operation inside of the loop. So now suppose the number of statements in a loop is A. There's A operations performed for each iteration of a loop. So for n iterations of a loop, that's an operations. And suppose all of these operations, n equal to 10, sum equal to 0, printing sum, suppose these are constant number of operations B. So how many operations do you have in total? An plus B. Now, as I told you before, we are interested in the growth of the algorithm. So that would be big O of n. And Finally, an example of polynomial time, which is in the form of O n to the power x. X, the smaller, the better. So n square quadratic time is much better than n cubed, and so on. Suppose you have two loops. You have an outer loop where I is going from 0 to n, and you have an inner loop where j is going from 0 to m minus 1. And you have a certain number of operations inside the inner loop. So for each iteration of I, there are m iterations of j. So for n iterations of I, there are m iterations of j. So how many times is this statement sum plus equal to 1 being executed inside the j loop? It's being executed n into m times. So let's suppose the number of statements executed by this loop, one iteration is again a. Then for n into m iterations of j, which is the total number of iterations, we are performing a, m, n operations. So now suppose n and m are equal. N into m becomes n square. So our complexity is in the form of O of n squared. At this point, I would like to ask if there's any questions and if everyone's okay with what I'm saying, then I'll proceed. Just type a confirmation, yes, or if you have any question, please unmute. If you don't have a question, just type yes in the chat. All right, I guess you don't have any questions then. So, like I said, time complexity is nothing but a function. So I've actually plotted it for you. So these are the most common time complexities that you're going to encounter when you're coding. So O of 1 is constant time. The growth does not change with growing n. Log n is better than worse than constant time, but better than linear time. Linear time is better than n log n, which is better than n square, which is much better than exponential time. Exponential time is usually the worst you can do. Not really, but most of the really difficult problems are 2 to the power n exponential time. So here's a relation where I have given you the relative ordering of the complexities, which performs better than which. Uh, Keep in mind, less than is actually better. So O of 1 is definitely much better than O of n square. The less the complexity, the better. The performance is better because the time is less. So we are trying to minimize the time. Keep in mind, don't get confused by the greater than. Greater than does not mean better. It actually means worse. I don't know how mathematically oriented you guys are, so I might skip this slide. Basically, it's a trade-off between factorial and exponential. Actually, factorial grows faster than exponential does, which means exponential is better than factorial, but only in certain case. So that depends on the base of your exponential. Exponential is in the form of x to the power n. So this depends on the value of x, if it performs better than factorial or not. Now is the interactive portion of this slide, of this presentation. I'm going to be sharing code snippets with you, and I want you to tell me what the time complexity will be. So let's start with the first one. Please type in the chat what the time complexity you think should be. Okay, Anushka says O of n. That is correct. Okay, now if I tell you, can you tell me the time complexity in terms of n and k? Can anyone tell me the time complexity? Yes, n by k. That is true. Let's go on to the next one. Is there anyone who didn't understand why it's n by k? Please unmute. So I don't mind explaining.
Can you explain me once this
Sure,
why it is n by k?
sure, sure. So have you seen it clearly? It is I from 0 going up till n minus 1 increment of k. So you have a you have a number line. This is 0. This is n minus 1. So this is actually n intervals. So we can also make this 1 and we can also make this n. It would be the same. So when we're, suppose k is equal to 3. So the first step would be from 1 till 4. The next step will be from 4 till 7. After that, 7 till 10. And this goes on until it reaches n. So how many times are you actually running the loop? It's the number of steps you've taken, right?
Yes, that would be n by 3. N
Yeah,
k by
n by k. Yeah, n by 3 in this case.
k.
So is that clear?
Yes, yes.
Okay, let's move on. Now, second one, in terms of n and k, please. Let's see what the complexity is. This one might be a little difficult for first years if you're not that much into maths. Any guesses? We have root to the power n to the power of 1 by k, n by k factorial. No. Any other guess? Anyone else? Log value. Yeah, it is log of n. So I think some of you might be confused with this one, so I will explain. So let's take n is equal to say 8, and let's take k is equal to 2. Okay. So how is I increasing? First I is 1, then it multiplies by 2 becomes 2, multiplies by 2 becomes 4, and then it becomes 8. And after that, I think the loop stops executing. So we can rewrite this as 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. Sorry, it's not plus, but I forgot this is a single loop, which means it's actually 2 to the power x in the form, the total number of steps. The final step, let's make it 2 to the power x. When is this loop stopping? It's stopping when 2 to the power x is equal to n. That's when we stop executing the loop. So what is x? Becomes log n to the base 2. X is the number of steps. This is 1 step, 2 step, third iteration, fourth iteration, fifth iteration, or x plus 1 iteration. We want to know the value of this, and that is in the terms of log. So the complexity is log of n, because that's the number of iterations in the loop. Could you understand that? The ones who gave a wrong answer, do you understand what went on? Okay. So let's go to the next one. This is two loops. Anushka says n factorial, Pragya says n square. Pragya, you might want to check the second inner loop. Everyone's saying n square. Okay, sorry, wait, no. Yeah, true. N square. That's the answer. I got confused. The other one comes later. Yeah. Does anyone, okay, the one saying n factorial, okay, it's actually n square. I can see why you might get confused, why you might think it's n factorial. I can see that. Yeah. So we have I, which is going from 0 till n minus 1. Or you can, actually, does it go from till n minus 1? Yeah, n minus 1. And then you have j, which goes from 0 till I. Okay? So let's see what's happening in the inner loop. So when I is 0, j does not, sorry, 0 to I minus 1. J does not really run because j is not closed and it's supposed to go up till minus 1. So it's not really running. When I is 1, j runs once. So that's one operation. Plus, when I is 2, j runs twice. And when I is 3, j runs thrice. And it goes on until I is equal to n minus 1. So j runs n minus 1 times. Do you know the summation of this? Summation of, yeah. So it's actually n into n minus 1 by 2, which is order of n square. So yes, this is n square time complexity. I think most of you got that. Some of you got a little confused. That's okay. Let's go on to the next one. N log n. Yes, that is correct. Does anyone want an explanation for this? Anyone who didn't understand why it's n log n? Please type in the chat if you've understood, then we can proceed. Otherwise, if there's anyone who's, please don't hesitate. If you don't understand, it's fine.
One more explain, please.
Okay, sure. So you have I from, sorry, you have I from 1 till n, say n, and it's multiplying by 2 for each time. Then you have j going from 0 till n every time, right? Yeah. So how many times is the j loop running for each iteration of I? It's running n times. How many iterations of I are there? It's multiplying by 2. It's the same as the one I explained in the previous slide. When it's multiplying by k, it was log of n to the base k, but now k is equal to 2, so it becomes log n to the base 2. And for each iteration of I iterates log n times. For each iteration of I, j iterates n times. So for log n iterations of I, there's n log n iterations of j. It's unitary method. One iteration n times, log n iterations, n log n times. So that will be your complexity. You can also think of this as a matrix, though I'm not sure if this pictorial representation might make sense to you or not. But if you work with 2D arrays, then nested for loops make a lot of sense. Suppose you have a matrix and I is your row value and j is your column value, and j goes from 0 till n minus 1, so that's n columns, and I goes from, well, I runs log n times, so you have log n rows. So how many cells do you have? That's the area of this rectangle. That's n into log n. So that's the number of, because for each row you have n columns and you have log n rows. So that's n log n cells. That would be the time complexity. I think the first explanation might be easier for some people. Second might be better intuitively for some people. Take whichever is convenient for you. And the final one. This one is my favorite. I want to see how many of you get it right. Any guesses? Dipandita says n factorial log n. Anyone else? Any other guesses? Or should I tell you the answer? Audrija says n square log n. Okay. All right. I think no one else has an answer. So I'll tell you the answer. So this one is a little tricky. This answer for this is actually n. It's O of n. It's linear. And I will explain why this is a little tricky. So in the Pragya says log of n square. If you know your log of n square, do you mean log of n square or log of n whole square? Because those two are different things. Uh, Either way, it's wrong, but log of n square would be 2 log n, which is just log n. So when you're doing complexity analysis, knowing your logarithmic properties makes, like, it really helps, because I'm going to be using one right now to prove that this is O of n. So we have I, which goes from 1 till n, and it's multiplied by a factor of 2, with each iteration. Then you have j, which goes from 1 till I, and it's actually a simple plus plus operation. Yeah. Let's take let's see what happens manually. So when I is equal to 1, j runs once. Okay. Then I is equal to 2. Yeah. So j runs twice. I is equal to 4. J runs 4 times. I is equal to 8, runs 8 times, and so on and so forth. When does the loop stop? When do we stop iteration? When I is equal to n. Okay. So then j runs I times. So now I is equal to n. So j runs n times. Once again, we can rewrite this as 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 plus n. Now, what is this n? We want to know how many iterations of I we've had, right? So let's suppose we've had k iterations of I. So for the first iterations, it's to the power 0, second it's to the power 1. So this would be 2 to the power k minus 1, right? So now 2 to the power k minus 1 is equal to n, which means k is equal to log of n, right? Almost log of n plus 1, but we are not really bothering with the constant terms. We don't really care what the constant term is. Now, do you know what this series is? It's a GP series, and we are adding it. So summation of a GP series, does anyone know the formula? It's 2 to the power k minus 1, I believe. Yeah. So this is the summation of a GP series. But we already know k is equal to log n plus 1. So we can rewrite 2 to the power k minus 1 as 2 to the power log n plus 1 minus 1, which we can write as 2 into 2 to the power log of n minus 1. If you know your logarithmic properties, this would be 2n to the power log of log to the base 2 minus 1, which is 2n minus 1, that is order of n, linear time. Did people understand that? This one is tricky, especially if you're new to time complexity. I did not expect any of you to actually get this answer on the first go. But did you understand it now?
N to the power log 2 or n, that is.
That is 2.
Oh, sorry.
Just correct that. Yeah. And when we are talking about log in computer science, it is log to the base 2. I am not going to keep mentioning that. So whenever I'm talking about log, just assume it's to the base 2, unless I mention otherwise.
The here you have taken n as equals to 2 in the last step
N
because
equals to 2.
oh, why?
I'm not sure which step.
Last step
Last
where
step.
n, yeah,
This one.
2 into n to the
Oh,
power log 2, that
yeah,
I
yeah.
cannot get.
That is a property of log. So if you have a log b, a to the power of log b, that's equal to b to the power of log a. That is a
Oh, then
property
oh, I got it, I
of log.
got it.
Yeah. And because you have log 2 and it's to the base 2, so that is equal to 1. Log 2 to the base 2 is equal to 1. N to the power 1 is n. So that's how we're getting 2n minus 1. Any other questions? Dipandit, I think you're unmuted. If you don't have a question, can you please mute yourself? Okay, thank you. This one was, no, it's okay. No problem. So this one was a little tricky. I hope you understood. And even if you didn't understand, I'm always there. You can ask me later on if you have any doubts. And this session is actually getting recorded, so you will be able to access this later on as well on YouTube. So that's the end of the quiz. Now I'm going to talk about something that might be a little out of scope for first years and slightly out of scope for second years. But honestly, you should be coming across these terms in like 1 or 2 years' time. I know many second years have not heard of amortized time complexity, but it is an interesting concept and a little advanced. So I will not be explaining it in great detail, but I will give you an example. Okay. One of the most common usages of amortized time complexity. So imagine you have an array. Okay. It's a horrible shape, but you get the gist. And suppose the array is filled. I have a 3 here, I have an 8 here, 0, 1, 2. It's filled. Now, I want to insert 7 into this. How would you do that? You have a full array, you want to increase the size to accommodate a 7. How are you going to do that? Any guesses? I don't want the correct answer right now, so you don't have to be pressurized to tell me the correct answer. I want a wrong answer. Appended at the end, Pragya, this is an array, which means it's not a vector. But what I'm talking about is actually the inner working of a vector. I am actually explaining how a vector works in like real life. Yeah. Double the size of the array. That is actually the correct answer. Good job, you know the answer. But we want to discuss the wrong answer because we want to appreciate why it's wrong. Okay, so I'm going to take a wrong answer. Suppose this array has n elements. I'm going to make another array which is going to have n plus 1 elements. Okay, and I'm going to usage of stack. I'm not sure. I think you are overthinking this. We don't really need a stack here. We're just working with arrays. Okay, so what I want to do is I want to copy the old array into the new array. So I'm going to copy the 3, the 8, the 0, the 1, the 2, and then finally I'm going to append the 7 at the end. Now I have space, no problem. When I'm copying this array, how many operations am I performing when I am copying this whole array, all the elements? What is the order of operations? What's the complexity of this operation? Yes, it's linear O of n operations because we are traversing this entire array from the beginning till the end, from 0 till n minus 1. So that's n times we are copying elements. So that's O of n complexity for copying an array. So let me just write this for quick reference. Copying array takes O of n time always. Now I am inserting one element, it takes O of n times. If I am inserting n elements, I want to insert n more elements. I want to make n insertions. What will be my total time complexity? What will be my overall time complexity? For one element, I am making O of n operations. For two elements, I will have to make two arrays. I'll have to copy from this old to the new. And then I'll have to make another array and I'll have to copy from this new to that new. So that's 2 times O of n operations. If I am making n insertions, I am copying this array n times. So that's n times O of n operation. That would be O of n squared. That's not good. This is not efficient. We don't want this. We want to do better than that. So, like Devapriya has said, we will do things a little differently. So instead of making the new array of size n plus 1, we're going to make a new array, a very large array of size 2n, twice of n. And we're going to copy all the elements from the old array till the new one. And now we have n spots free. So if I'm making one insertion, I can just easily append it here. So for making one insertion, what is the time complexity of my operations? When I am making a new array of size 2n, I am making one insertion. My time complexity is O of n because I'm copying the entire array once. But if I'm making n insertions, then even then my time complexity is O of n. Because now when I'm making another insertion, I'm just inserting it here. Suppose I'm inserting a 13 here. I'm inserting a 4 here. Inserting a 10 here. Okay, and so on and so forth. I can make n more insertions without copying this entire array even once. I just need to copy it once and I'm good to go. I can make n new insertions at O of one time, constant time. So for one insertion, I'm taking O of n time. For n insertions, I'm taking O of n time. So what is the average case? On an average, how much does each insertion cost? On an average, each insertion would cost n by n, O of n by n, which is O of 1. And this is called your amortized time complexity. O of 1 amortized time complexity. What does amortized mean? Amortized means you are a particular operation takes a lot of time. It's very expensive only in certain situations, but for most situations it is not expensive. So we are making an overhead cost. We are anticipating that, okay, I'm going to need this space. I don't want to make this a one time operation. I am anticipating the future that I might want to make more insertions later on. And in such a situation, it would be more economical for me to make the array of a larger size. And so I'm getting O of 1 complexity for insertions, when in actuality, that is not the actual case. This is O of 1 is not the case when you're making one insertion. And that's what makes amortized time complexity so interesting. And if you, some of you might be C++ coders, and I am sure you've used vectors, and you all have the conception that the pushback operation of a vector is O of 1 time complexity. It takes O of 1 time. That is actually partially true. It is not O of 1 complexity. It is O of 1 amortized time complexity. And this is exactly how a vector works in C++. The process is called table doubling. I'll just, and it's used in hash maps, it's used in vectors, and amortized time complexity. This is the most common example. There are more, but it's a little advanced. The topic is a little advanced. So I will be explaining just this one, just to give you a good idea of how it works. And finally, this is completely out of your scope, so I am not going to talk about this. I think second years learn about this in third semester in discrete mathematics, and this is a topic of theoretical computer science. It's called NP completeness. So we have models of computational complexity. P is polynomial, E is exponential, and then you have something in the middle called NP, which is non-deterministic polynomial. If you are interested, I have included a link to an MIT lecture by Professor Eric Demain. He is a brilliant professor, and this is a brilliant lecture series. So I would totally recommend you to check this out if you are clear with your time complexity concept so far, if you've understood everything I've told you so far, and if you're interested in theoretical computer science and you want to know how it works, you want to know more of the theory. So you should totally check out this video. I will be sending you the slides later on, so you can find this video then. Otherwise, if you need help with finding, I'll just write the lecture series. It's MIT OCW 6.006 lecture 23. Okay. So if you're interested in knowing about time complexity, NP model, P model, you should check out this video. And we've reached the end of our presentation. If there's any questions, I will be taking them right now. First, tell me, how did you like the session? Did you learn something new? Was it interesting? Any feedback? Any questions? Any comments? All right. Do you feel more confident about time complexity now? Do you think it's something you'll be right? If there's any questions, you should ask now, because it's fresh in your mind right now, and it's fresh in my mind right now as well. So if you ask me later on, I'll have to scramble to get back into this frame of mind. If you have any confusions, any part you want me to repeat, any part you felt you couldn't really follow, all right? Okay, so I think we can call it a day then. That marks the end of the session. We have about 15 people today, which is not bad. Thanks for joining. Yeah, thanks. You guys made it interactive to some extent, and that was really important. That was needed. So thanks for joining, and I will be ending the session right now. All right, thank you.